Perfect. All right. You all ready? All right, so we were drawing some pictures yesterday. We're going to continue drawing pictures today, and then we're going to learn a new way to represent energy. And then we're going to do a little bit more practice. And then if there's time, we're going to do something cool. Are you ready?
Sure.
All right, so get out your papers, get out your colored pencils or pens, or if you have one, a designated pencil for Phys, get that out, because you're going to need that for sure.
Michaela, you kind of shine.
All the time is her time to shine.
Thank you, Mr. Pettit. I
No
appreciate it.
problem. All right, this weekend, the one thing I'm going to do, I need more whiteboard markers. I'm going to get the colors I want.
I had this right one. That took from my finish.
All right, so where did we end yesterday? If you remember, we were taking this ball, and not this ball, we were taking a different ball and we were bouncing it. And what do you notice about the height of the ball that it comes to versus the height that I released it from?
Comes to almost the same height. Or like a little shorter than it.
Does it come back as high as it did?
No.
No. Is it losing some energy from here to the next one?
Yes.
Totally, right? And the question is, where does it go? Okay? So I'm going to drop this ball, and it's going to go boop, boop, okay? And so we're interested in the first two bounces. Excuse me.
Numbers or letters? I think it's the card. I don't have the card.
Okay? So we've got 5 locations in time and space. So we're going to draw 5 pies. What should be true about the size of the pies? What should be true about the size of the pies? Yes?
They should all be the same size.
Absolutely. Why?
Because energy cannot be created or destroyed.
Actually, that is true. That is 100% true. Yes. Normally we just say that the total amount of energy stays the same, but I'm not sure we're in the process of creating or destroying energy, but I like what she had to say, right? It's in the spirit, right? You can't create new energy, you can just make it look different at different times.
Yeah.
Right? Okay. All right. So what are our four energy types that we're dealing with here?
Gravitational.
What did you say?
Gravitational.
Gravitational, that is definitely one.
Kinetic.
Okay, listen, I grabbed 2 color markers and you said neither of those two.
Kinetic energy.
So this is the energy, we say it's kinetic, that's the energy of motion.
Yes.
Okay. And that one is, we're going to do it sideways. All right. Whoa, uh-oh. Who is it? Who is it?
Shouldn't be me.
Who's in before?
Please don't be me.
Good morning, 106. I'll send him right now. Mr. Scott, you're the big winner. Go see Mrs. Vernier with all your stuff. Again, look on the school Jeep for the update. I'm going to record and post the videos. Okay? You're going to want to watch them. We're going to assess next week, and I don't want you to be, I don't want you to miss out on it. Okay? All right. So we got gravitational.
What day next week?
I don't know. Someday. Okay? So this is the gravitational energy. This is energy stored in the gravitational field. The higher up you are, the more gravitational energy there is. Okay? What else?
Elastic.
Yes, you can store energy in springs and rubber bands, right?
I just didn't think it was in this instance.
What's that? You didn't think of what?
It's in this instance.
Oh, well, it is. And just in general, these are the 4 we deal with. What's the last one?
Thermal.
Yes! Yes! So the thermal energy, so yesterday, what we saw is you can get thermal energy either from a collision or from some rubbing with friction. Is that cool? Actually, it's something really interesting. I will show you over here.
Like silent or something. You have ASM or something?
I do know ASM.
Flex. I don't. Guess you probably don't.
Uh-oh.
If I can leave school because someone got COVID, I'm mad. If I have to go home because someone got COVID, I think I'm kind of mad about it. Will that, Andrew? I don't know. Depends on who. Yeah, there was. And they.
That was just wet. Or to wait for them to dry.
Why are they wet? Oh.
Yeah, and get their attention. Oh, that's too funny.
All right, we'll talk about that in a second. We'll get to the balls here in a second. All right, so you're dropping the ball here. You're dropping it from rest. What's the energy situation in number one here?
Maybe half gravitational, half kinetic.
If it were moving, it would be kinetic, but
Oh,
we're
it's
dropping
not-
it from rest. Go
It's not
ahead.
moving yet? Okay.
Go ahead. You can just talk out
I
loud.
also.
There's only like 4 of us here.
I know, our side of the room's holding out strong.
I know. Good work.
Good job, everyone.
I think it's gonna be half gravitational and half elastic.
So right here,
Would any be fully gravitational?
I think fully elastic.
so if it's elastic, it has to be pulling or pushing on some springs or something.
Oh, so.
Oh, you have it up
okay.
there.
Okay, then yeah, it's gonna be full gravitational.
I think it's only gravitational.
Mr. Panda.
I know. Now,
Trick question.
so here's what happens. It hits the ground, right? Now, if you've ever seen a ball, like slow motion video of a ball, like a bouncy ball or a golf ball or a squishy ball or something.
I've seen those.
What happens when like a golf ball hits something or a club hits a ball? What happens to the ball
It
physically?
squishes.
Have you seen this happen?
I've seen
like
it.
slow motion video of it?
The golf ball is.
It's crazy how much it
I
squishes.
didn't think how much it would squish.
But it squishes, and then what's it do?
It goes back.
Then it rebounds, right?
Yeah.
So what's inside a golf ball?
Rubber.
It's rubber bands. It's literally like wrapped up rubber bands. And so what happens is, when it squishes, all that energy is stored in the rubber, but then it re-expands. So when it's in contact with the ground, and do you think it's squishing and storing some energy there?
I think so, yeah.
It totally is, right? So what kind of energy do we have in this one? Oh, she's back! She's done it! She has done it!
Who had it?
I don't know.
Everything good?
Yeah.
Fantastic. Look at you, hero. Look, hold down her side of the room. Good job, Sarah.
Good job, sir.
Oh!
You missed. So close.
I'm sorry, I'm gonna go back and watch these videos for fun.
All right. So Sarah, what we're talking about is we have a, in this case it happens to be a golf ball. And when you drop it, what you'll notice is it never comes back up to as high as it did before. But it also doesn't just hit the ground and stop, right? So we know that there's some energy stored in the ball, and then we get some back out, true? So in the picture we have here, it's all gravitational to start. What about at number 3? All right? I'm going to say 3 is about 2/3 the way up.
What about the second circle? What about number 2? Oh no.
Oh, man. Okay. So, if this is 2/3 gravitational, what's the rest?
Elastic.
So, it's elastic, but
Oh.
it's squishing in contact with the ground. What about number 3?
Kinetic.
It's not moving when it gets to the top of its path.
Oh.
Isn't it
Thermal?
always moving though?
Okay, see? So this one, we're going to say it's just going up and down, but that's hard to draw here, so I extended it out. We can see what it looks like if it's bouncing and moving forward after, but let's just say this one's just going up and down.
Oh, so not just up and down. Not
Yeah, but that was such an astute observation. I really appreciate that. All right, so let's come to here,
Would be thermal?
okay? So when it hits the ground, a bunch of thermal energy is generated, true?
That's correct.
And in fact, it is a third. Okay? So a third of the thermal energy, a third of the total total energy gets converted to thermal energy. Okay? And then what's the rest then?
Elastic.
Good. The rest is the elastic because the ball is squishing. So then when I come to here, all this elastic as it goes up is kinetic, and then that kinetic goes to gravitational. But we're missing the third because it was converted to thermal a moment ago. All right. What about the last one?
Oh.
Yes.
Half gravitational, half down.
So you can do half. I like half. That sounds good to me. So it's back up at the top of its path, so it's not moving anymore. And where's the rest?
In the thermal.
And then what about this one then?
One half thermal, one half elastic.
So every time you hit the ground, more thermal energy was generated. But if it's in contact with the ground, it's squishing, right? So what I like about this is your gravitational energy goes with the height of your object. Okay? Your gravitational energy goes with the height. So we have lots of gravitational energy, less here, even less here. True? So what does it say about the height of your ball? It's high, then it's medium, then it's low. See how that works? So gravitational energy goes with height. What about kinetic energy? What does kinetic energy go with?
Energy goes with movement.
What's that?
With movement?
Yeah, so how do you know if you have more or less?
It's velocity.
If you're going fast or slow. So we're trying to understand whether or not collisions generate enough thermal energy. All right, so clang them together. Perfect. I'm going to put the paper in between them. Go ahead. So you see there's a little hole there. Okay, do it again. How did that hole get there? It burned it. Smell it.
Yes, right.
So by clanging these together, you're generating enough thermal energy to burn a cute little hole in the paper. How adorable is that? What's that?
Choking.
And here we are. Here's the paper. And then when you clang them together, there's enough thermal energy generated. I can't do it by myself. Well, I'll do it right here.
Oh, I can hold it. Or not. I could just not hold it if you want.
Cute little hole. There. All right. Okay.
I can make a pie.
How do you guys feel about that?
That's pretty
Feel good
rad.
about that?
That's pretty cool.
Is that cool? All right, let's do another one. So have you ever been to an amusement park with a roller coaster?
Yes, I have.
You say no? You've never been to an amusement park with a roller coaster?
Oh,
Never went to Cedar Point in 8th grade.
no, I didn't. I'm scared of roller coaster.
I mean,
Wait,
I
how
was,
could- you've never been
That
on
doesn't
one?
surprise me.
I was too when I was
I
forced to
don't
go
know
on
what
them.
you
Oh.
think. I
I
forgot.
was always tall enough at a young age, so I was forced to go on them by older.
Oh, that's
Oh,
hilarious.
Yeah.
that's so unfortunate.
That is so-
How hard.
Yeah, I was
Wait,
a,
Wait,
too
can you go
short
on the
to go
top of the
on?
dragster, or are you too tall for that?
oh, I'm too tall for some rides, yeah.
That's
Are you
actually
really?
Yeah, I mean, well, some of the new harness ones that have like the rubber on it, they like crush my spine, so they cause medical problems, so I don't go on them.
How tall are you?
6'7".
Are you really?
Yeah.
Lord in heaven. Oh gosh. All right, here we go.
You're
You're
6'7"?
literally over
Yeah.
a foot taller
I
than
thought you
me.
were 6'5".
No, I'm 6'7". Yeah, they cause
Oh my God.
spine problems,
Yeah.
so I don't really go on too many of them.
Because I know on top of the dragsters, the tallest one can be is like 6'5".
Yeah. Because if you go, because that's like what the height of the chair, so you'll get whiplash.
Oh,
And break a neck, which I
You
don't want
did
to do.
break your-
Yeah, I could
Yeah, you
possibly go
must-
on.
You didn't like your roller coaster?
What?
He drew a roller coaster when you were right.
Yeah, it was a good one too. It was pretty good.
Doesn't South go to Cedar Point for physics?
They used to. They haven't in a couple years.
Pre-COVID.
Oh,
Imagine.
We used to too.
Just a class at scale.
I wish we did.
On a roller coaster.
Well, you know, it became problematic because what was happening was we were planning this trip and we would plan it in like September. And everyone would be all like fired up to go and we'd start collecting all this money. And we'd have all this money and then at the end, people were like, well, I don't want to go now because it conflicted with sports and it conflicted with all these other things. And we're like, but you gave us a non-refundable deposit. Like I bought the buses already.
Did you guys just go for a day or two?
Just one, and it's plenty, like, we would leave here at like 7, and it doesn't open till 10. So we'd leave here at 7 or 8, get there by 10, ride the rides till like 6 when it really started closing, and then be back by like 8:30 or 9. It was a great time, but then one year we took one bus, and then we took like 2 buses, and we took like 3 buses, and the next year we're like, let's go again. And then all of a sudden, like, we didn't have enough for 2 buses, and then when you were like, when there was only like 20 kids wanted to go and like 120 kids were here with subs, the administration's like, that doesn't seem like a good use of people's time, so we stopped doing it.
I love Cedar Point.
I don't even know. All right, here we go.
Fun.
Here's our roller coaster.
You go there with your kids at all?
Okay, what's that?
Go there with your kids at all?
Have I gone with my children?
Yeah.
They're still too young.
Ah, darn.
My oldest is only 10, and he's over 4 feet, but not
It's not
over.
58 inches,
He's not. Is he 52 inches now? They're short like me, so they don't.
so I think they run bigger rides.
It's alright.
All
I
right,
was tall
are you
enough.
ready?
I was tall enough at like 8, so
And then you just got.
yeah.
Then you just went. Now you're
And,
Here's our roller coaster. Got it? So there's 1, 2, 3, 4 instances in time. Okay? So let's draw the picture. Let's draw the pies. Now, we're going to pretend this is a fancy,
no,
no friction roller coaster.
those are pretty rare.
That's good.
They only exist in my head. Okay, they only exist in my head on the physics classroom board. All right? And we're going to say that it starts from, well, can it really start from rest? Let's say it starts from rest. It'll be easier that way. Let's say it starts from rest and goes. Did you fall?
In track, yeah.
Oof.
Yeah, I hit a hurdle and then I kind of
That is all over.
ate crap and I hurt the hand.
Still did good.
Yeah, it was in his race. I hurt the hands, I scraped the knee.
Hey,
It was kind of bad.
Brutal.
now you have a straight account.
Thanks. Who was that?
What's happening right now?
Who was that?
I don't even know. I'm good. Probably bigger.
I would think CJ, but I'm not sure.
It was a blonde kid.
This might be CJ.
Pretty much one of those kid I know back from my Waterford. I'm literally saying this while we're getting like
Yeah.
Wait, you
You know what,
used to live in Waterford? Waterford.
All right, let me see your pies. Don't wait for me, I want you guys to fill them in.
Oh.
If there's no friction, this is not
There's no friction, that makes it easy. That makes it easy.
Are you gonna
And is it
come to
moving in the
track?
first picture or no?
Are you gonna come to track? Track would be last.
Am I gonna what?
Do you come to track too? Because the track would be last.
So we're not, we're just gonna say that the car is just rolling along the track, and let's make the track rigid.
Okay.
So it doesn't like give it all, let's just
Okay.
say.
I'm not sure how it is. It stopped at the number 2, or is it going?
It keeps going. It's not friction, remember?
Oh, my bad.
So the first thing I wanna do is, I just wanna use our understanding here. I'm gonna label these A, B, C, and D. All right, I want you to rank speeds fastest to slowest. Okay? So do that on your page first. Rank the speeds. What do you think? Where's it moving the fastest? Where's it moving the slowest? Where's it in between? All right, do that on your sheet now. Okay? Got one by you there, got enough room for me over there.
Martha, right? Okay, I think I got it.
Did you rank them?
I'm struggling with it now.
Are you?
Yeah, I haven't been on a roller coaster since 2013.
All right, you can see the roller coaster I drew on the board.
See if I
Probably
didn't tell me how fast it's
0.5.
going.
I haven't been there.
Bro, I still have my season pass.
I haven't been there in 4 years.
I've been in it for 3 years now.
All right, if you had to guess, where is it the fastest?
B?
Definitely the fastest at D.
Oh.
Okay? Where is it the slowest?
A.
A?
Yeah, because it's not moving. We're releasing from rest. So there you go. All right, what about the other two?
Would B be the second? Yeah.
and C would be third.
I thought B was first. Not B. Haha. Pun.
Now, one of the things we know is that the kinetic energy is related to the speed, correct?